In any industrial setting, the absolute objective of operations management is clear: to maximize system output reliably and predictably. Yet, companies routinely pour millions of dollars into upgrading specific machines or software, only to find that the total volume of finished product remains exactly the same. This misallocation of resources results in wasted capital expenditure and makes it impossible to build realistic planning commitments for the market. The mechanism dictating this systemic failure is singular. It is known as the bottleneck. The purpose of this analysis is to locate that definitive limiting factor, allowing us to direct improvement efforts exclusively to the point where they mathematically force an increase in total output. Attempting to optimize an operational system without first identifying its ultimate constraint results in zero net gain, making global improvement a mathematical impossibility. Formally, a bottleneck is defined as the resource, process step, or constraint within a system that possesses the lowest effective capacity. This single node acts as a strict physical threshold, governing the maximum throughput of the entire operational network. Consider a standard manufacturing line with sequential processing stations. If an upstream machine processes 60 units per hour, but the downstream machine only processes 30, flow is compromised. Total output is permanently capped at 30 units per hour, neutralizing the excess 60-unit capacity. This mechanism applies equally outside of physical manufacturing. In service operations, a single approval manager requiring manual sign-offs acts as an identical bottleneck, artificially constraining the velocity of digital workflows. A system's true capacity, therefore, is never an average of its constituent parts. It is an exact, unyielding reflection of its weakest link. This diagram outlines the basic architecture of an operational system: inputs, process steps, and outputs. As you can see, multiple lines of input are physically restricted as they converge into a narrow central ring. This architecture establishes the principle of flow dependency. Because the steps are sequential, the operational speed of the fastest nodes is entirely subjugated to the limits of the slowest node. Due to this strict dependency, there can mathematically only be one true bottleneck dictating throughput at any given system level at one time. The primary diagnostic symptom of this dependency is highly visible: a massive, sudden accumulation of inventory or tasks directly upstream of the constraint. This specific buildup of work in process acts as a physical barrier. Every new unit entering the system must now wait in this expanding queue, which dramatically increases the total lead time required to convert raw materials into finished output. Constraints are dynamic. If engineering improves the throughput of the current bottleneck, the system's limit will naturally and immediately shift to the node with the next lowest capacity. This accumulation of work in process is the direct structural symptom of a constrained flow architecture. The governing intellectual framework for analyzing these system limits was formalized as the theory of constraints. This diagram illustrates the theory's core mechanism. Adding capacity to a large non-constraint node yields zero improvement to system output. Aggressively running a non-bottleneck simply feeds excess work faster than it can be processed, clogging the flow. Maintaining balanced flow requires specific nodes to remain idle while the bottleneck catches up. The bottleneck operates under completely different rules. Lost time at the true constraint is lost throughput forever. It cannot be recovered. Because of this outsized impact on total output, the bottleneck must be rigorously protected from upstream demand variability and process disruptions. Local optimization is an illusion. True systemic optimization requires subordinating every single peripheral process to the strict governing rhythm of the bottleneck. These principles extend far beyond theoretical models and dictate the limits of macro-level industrial management. Identifying the constraint is the mandatory first step for accurate production scheduling. You cannot balance a line or release materials efficiently until you know the exact processing rate of the slowest node. This exact constraint data must then flow upward into sales and operations planning. Without knowing the firm limit of production, sales teams risk making market commitments that the factory floor mathematically cannot fulfill. Constraint analysis also governs capital investment. High-return capacity expansion is only achieved by directly widening the bottleneck, ensuring new equipment actually generates higher volume rather than just building faster queues. Business strategy cannot be divorced from operational limits. Ultimately, a company can only sell what its bottleneck can process. In modern global supply chains, isolating this constraint is rarely a straightforward static equation. When a facility processes work in massive, infrequent batches or lacks granular sensor data at every station, the movement of material becomes opaque. This lack of visibility allows structural constraints to remain hidden from executive management, appearing as general delays rather than specific bottlenecks. Furthermore, highly volatile market demand creates dynamic operational environments. As product mixes change and supply shocks occur, the bottleneck does not stay fixed. It rapidly shifts back and forth between different operational nodes. This volatility is forcing global operations to abandon high utilization metrics, prioritizing instead the creation of systemic resilience and consistent flow. Static efficiency models are now obsolete. Modern operations require real-time, dynamic visibility to track, isolate, and protect these constantly shifting constraints. This requires unlearning one of the most pervasive misunderstandings in operations, the false belief that the busiest resource is automatically the bottleneck. If every machine in an interconnected system is forced to operate at 100% utilization, the system will mathematically collapse under the weight of queue buildups and minor variability. This debunks the costly myth that adding capacity everywhere solves production issues. Any capital spent widening a non-constraint is financially destructive. It absorbs funds without yielding a single additional unit of output. Maximum utilization is not a metric of high performance. In complex systems, 100% utilization is almost always a symptom of systemic inefficiency. To definitively locate a system's true bottleneck, professionals use a concise diagnostic framework. Ask 3 questions. First, if this step stops, does the whole system stop? Second, if we improve this step, does total output increase? Third, where does work in process accumulate the most? Review your own operational data. Do your key performance indicators accurately measure true systemic flow, or are they merely rewarding local efficiencies that clog the network? A bottleneck is defined strictly by the limitation of flow, regardless of how difficult the labor may appear at any specific station.